Okay, thanks for the invitation. So I'll first start describing the object. So I'm going to talk about like G. It's going to be a simple Lie group or semi-simple, but just to keep it simple, it's going to be a simple Lie group. And so in simple Lie group, and in my mind is always SLNR. Okay, and gamma is going to be a lattice, so a discrete subgroup such that the quotient here is going to be, so it's acting by isometries in the right, and this thing has finite volume, and in my mind is just SLN. See, okay, and what else? Let me see. So I'll first start. What is this? Yes. So well, a simple example here is just SL2R that for me is the group of isometries of hyperbolic space. And okay, I'm going to describe a couple of subgroups that I will use of this. So here for SLNR, there is this subgroup that is called the Cartan subgroup, such that these things are equal to 0, and there's a maximal compact subgroup of SLNR that is going to be SON. Okay, so first I'll talk about Mosto rigidity, and here, so I'm going to take S a surface and pi1 of, so I call gamma pi1 of S, and if you have a discrete or homomorphism from these two SL2R that is discrete, so then this is equivalent to have a hyperbolic surface, a hyperbolic metric on the surface, right? So this hyperbolic metric on S. Okay, but and there are many hyperbolic metrics on a surface of, so here the surface has genus greater than 2, closed surface. So and this is like I'm going to write wrong this name. Is it like this? No? Okay, nice. Okay, so this is Teichmuller theory, but when is a hyperbolic manifold of more dimension, there's not so much flexibility to give a hyperbolic metric. So this is what is Mosto rigidity. I'll state it here, saying that if you have some, so you have phi of gamma 1 and gamma 2, two of these groups, and this is an isomorphism of groups, then this phi extends to the whole groups G1 and G2. Okay, so and usually is just like a conjugation. So or basically conjugation. So if you, this was like a corollary is that if you take the group of isometries of hyperbolic 3 space, right? And you have a manifold, and M is a manifold. M has a hyperbolic metric. Then that metric is unique. Then this metric is unique. Okay. So this was.
Sorry.
Yes.
In this formulation of mass over to D, what are the hypotheses on G1, G2?
Yeah. So here the hypothesis is that, well, G1, let's say, is simple, sure, lattice, and is different than SL2R. Just different than SL2R. GI different than SL2R. Okay. So I'm going to, well, say like this thing that is Margulis superrigidity. That is a general of this, and it states the following. So I'll just state it in the case of SLNZ. It states that if you have some homomorphism, group homomorphism from SLNZ into some SLMR, then this thing actually comes from some continuous. So here this thing is a continuous, very nice thing, right? So it's actually the same true here. So there is like some, here is the inclusion. So there exists this phi, the extension that continues. Okay? So this is not exactly true, but it is true up to finite index. What is called? Okay, but
what is assumed about the given map phi?
It's just a group morphism. Okay, that, and well, I'm saying that it's the image of phi is infinite. The image of phi is infinite, and there I say that up to finite index, then this is.
What is up to finite index?
Is that so this corresponds to like this kind of manifold. If you take a finite cover of this, then you take. Then the fundamental group of that's a finite subgroup of finite index subgroup. Okay, so there is like this, or there's a subgroup such that the quotient is finite. Okay, a subgroup of this such that the quotient is finite. Is that making any sense, or?
I think he's asking.
You're asking what is finite index subgroup, right?
No. Well.
No. Sorry. Sorry.
You take a phi from SLNZ to SLM.
SLMR for.
Then I want to ask, does this extend to SLNR?
Yes.
And you're saying
it always extends.
Up to what?
It always extends. That's the thing. It always extends.
Okay.
Yeah. So if it doesn't extend, it's for stupid reasons. Okay. It's basically being like, okay, maybe this was, you can map it into a finite group, and this finite group acts in SLMR, but you can extend the action of the finite group, something like that.
So if you were to replace SLNZ with a finite index subgroup of SLNZ, does the theorem still hold?
No, it's still true up to finite index. Okay.
What do you meant by true up to finite index?
Oh, yes.
I mean,
That the homomorphism, this homomorphism is going to be equal to phi in a finite index subgroup of SLNZ. Okay? Oh, that was the question, right? Okay, sorry. On M, so here there's no hypothesis on N. Yes, thank you. So the hypothesis again is that N is greater than 3. Just this hypothesis. So it is not true for N equals 2 is false, because SL2C, well, this thing is just the fundamental group of this like modular surface, or, well, it's almost a free group, and you can map a free group into any way, and you can't extend like this thing, right? So So okay, so like a corollary of this thing is that if m is so if m is smaller than n, then the image is finite. Okay, image is finite. So yeah, and in the case of equality, well, it's just given by a conjugation by the usual inclusion. So now I can explain what is like this Zimmer, like conjecture or Zimmer philosophy. So I'll just talk about like the Zimmer program philosophy. Is that I don't know if I'm writing. It's philosophy. Yes, no. That's how you write philosophy, right? Okay. So it's saying that if you have some action in some manifold, so here M is going to be a closed manifold, and these are going to be the infinity diffuse. Then phi comes from like a nice algebraic construction. Okay, so this case where when you have SLNC acting linearly in Rm, in some big Rm, then it comes just from some nice embedding here. So I'll give a couple of examples. So one example is you have SLNC acting on Rn, right? And this action, so because it's linear, it induces an action in Rp of n minus 1 just by projectivizing, but you can also get an action in Sn minus 1 just projectivizing by the positive rays. And so the conjecture in this case is that if you have an action in a manifold of dimension equal to n minus 1, then the manifold should be either this or that, and the action should be conjugate by some diffeo to one of these standard actions. Okay, so that's not yet proven. And so this is one example, and another example is SLNC acting on the torus. And okay, so this is, yeah, another action, and the good thing here is that you preserve here like some kind of volume. So the conjecture is that if you have a volume preserving action of SLNZ in some manifold of dimension n, then the manifold is the torus, and the action is conjugate to the standard action. Okay. So, and so I'll state more or less. So in the case where m has dimension less than n minus 1, because this is the dimension of smallest linear representation, what is expected is that such an action, well, what was expected is that such an action didn't exist, and that's what like we proved. So, well, I'll say that this is joint work with Aaron Brown, David Fisher, and it's also based on work of Shiren Wang and Federico Rodriguez Hertz. So the theorem is is the following. It says that if you have some, so what I'm going to state here is true. These might be like false up to something, but this one is true. So that if you have this and the dimension of M is less than n minus 1, then the image is finite. Oh, no, sorry, just diff. Closed compact closed manifold. Yes, or compact manifold also works. But n is at least 3. Yeah, n is always greater than 3. Okay? So, yeah, yes, so we proved this for SLNC or gamma when gamma is co-compact, meaning that quotient over here, G mod gamma is compact. But like co-compact lattices are like very horrible to write. Or yes. So example, I mean. Okay. Yeah, so Polterovich proved when SL3Z acting on a surface by volume preserving thing, so prove that it doesn't exist. Yeah. So when you put like here the assumption vol, you can take this less than n. Yeah. Yes. Okay. So I'll state why this like Zimmer conjecture. So this was like known as Zimmer conjecture, and I state why did Zimmer state the conjecture. So he had like this theorem that is called Zimmer cocycle superrigidity. That is a generalization of this thing that I mentioned. So I'll mention just like of this Zimmer cocycle superrigidity is that if you have an action of SLN Z acting volume preserving, so M vol and the action ergodic, meaning there are no invariant sets of measure between 0 and 1, then and dimension of M is less than n minus 1, then the action preserves then SLNC preserves a measurable Riemannian metric. So I'll try to explain in a little bit what is this thing, the measurable Riemannian metric. Okay, so to explain this, I'll first. So what he was. So I'll just say it here that if this measurable metric you make it smooth, then this theorem follows easily. Okay. Then theorem follows easily because you know, if you have if you're preserving a Riemannian metric, your action is by isometries, and isometries are like really nice diffeos. Here the problem is that these diffeos might be like, or have like some hyperbolic behavior, hyperbolic fixed points. So diffeos like could be like super crazy, right? So that's just when you get like something or so much structure as a Riemannian metric, then it's done. Okay. So.
But is there some dimension
yn minus 1?
Yeah, I mean, in the context of the argument you were kind of alluding to, that if you have a smooth metric.
Yes, it's exactly that the group.
Isometries on a manifold of this dimension.
Yeah, the isometries is bounded by, I don't know, it's n times n minus 1 over 2 or something, n minus 1 times n minus 2 over 2 here.
Okay.
Right, and then you use like this Margulis superrigidity, that is like the classification of these actions in Lie groups. So.
The isometry group is a compact Lie group, so
It doesn't follow. It doesn't follow like immediately from there, but it's for what I said. But it comes from there. Okay. So if you replace here by, I'm skipping things that I don't want to talk about because it takes some time. So So now I'll describe a construction that is very common here, and it allows you to replace your gamma action with a G action in a different manifold, and it's like a mapping torus. You know, when you have like Z acting on a manifold, you can construct this mapping torus. So this is like the version for Lie groups and more general lattices. So this is the suspension of an action. So the suspension is going to be this manifold, that is G cross M modulo okay, and gamma here in my lattice. So I'll put gamma, but in my case, in my mind, is SLNZ. Okay. So it's like geometrically, this thing is going to fiber over G mod gamma, and how it looks like is I have my G mod gamma, and here at each fiber I have some copy of M. Okay, and this has an action of G here, so G action. Okay, so and how is the action in the fiber? So if I apply like some element G, and this element G like correspond to some loop here in the fundamental group, what it's going to do in the fiber is just going to be acting by the diffeo given by this element of the fundamental group that is in gamma. Okay. So now I'll state like this Zimmer cocycle superrigidity, that is, so Zimmer cocycle superrigidity says that if, I first have to say what's a cocycle. So a cocycle is some kind of map from, so here is going to be G cross some space that is going to be my M alpha for me, but let's call it N into some Lie group. So, and that satisfies the chain rule. That satisfies that phi of G1, G2, P is phi of this is phi. Okay, so in our example here, H is going to be S of L of like the dimension of the fiber, so SL of dim of M is going to be the derivative, the fiber derivative of R. G is going to be my original, so this was SLNR, G of SLNR. And phi is going to be the fiber derivative. So it's going to be d of phi of GP is going to be d of G of P here in the fiber. Okay? So and here let's suppose that all these things are like trivial. So the tangent bundles are trivial, but because this theorem it's about something measurable. So it says that the following. In this contest, it says that this cocycle up to some change of coordinates, so this derivative up to some change of coordinates is going to lie in a compact subset of SLNR. So it's going to, I'll state it here, is that there exists phi, some, and here I'm going to assume the action of G into N is ergodic. Ergodic and preserving some measure with respect to some measure mu. Respect to some measure mu. So it says that there exists like a measurable map phi from your space that is like this change of coordinates such that if you apply the change of coordinates, if you defined this cocycle, that is another cocycle, then this cocycle is then the image of phi1, then either the image of phi1 lies in a compact set, so in a SO of the dimension, in this case, or SO of dimension of M, or the other case is where phi1 doesn't depend on X, on X. So it's like the action in the torus, the derivative doesn't depend on the point because it's just a linear action. So it says that phi1 is a homomorphism from G to H, group homomorphism. So okay, this might be I'll say that. So what it's saying is that if you have this ergodic action, not by gamma but by G, then the derivative you can either like trivialize it or make it into a compact subgroup by this measurable map. And here's the measurable metric comes from this map being measurable. Okay? So this is equivalent to having this change of coordinates being continuous is equivalent to having a Riemannian metric. Okay, so maybe I forgot to say something about the suspension that is kind of important, is that when you have like the suspension, like so every property for the action here has like some equivalent here. So if gamma acts on M, like preserving a measure, then there's a corresponding measure here being preserved by this. If the action was ergodic, then you get some ergodic action here, and still, like if you have a metric, here you have a fiber metric that is being preserved by this action. Okay. So what I'll try to explain now is more or less like the ideas in the proof of this theorem. Okay? So the idea is again like finding this invariant metric, but the way it's found is not towards like generalizing this result, but it's a bit different. So So the idea of the proof is the following: is we're going to like take some metric. You can take the metric on either M, or you can take like some kind of like fiber metric over this thing, metric in each of the fibers, and then I'm going to try to find an invariant metric by averaging this metric over the group. But then, some average procedure is going to give me a G invariant or gamma invariant metric on, well, I'll put it G invariant fiber metric, or metric on each fiber that I'll call fiber metric on M alpha. Okay, I'll start with a fiber metric on M alpha. So, but of course, like the problem is when you want to average. If you have a finite group, you can always average a metric and obtain invariant metric. But the problem here is that, of course, like this group, you don't have first. The group is non-amenable, so that's a problem. But the group it satisfies some averaging, like well-known thing called property T. So that implies that like averages, when they converge like really fast. So that's one thing that is going to be give you the average procedure, but also you need like some bound in the things that you want to find, or some bounds in the things that you're averaging. So what I'll try to say is like what exactly conditions we need in the action. So the technical like theorem is the following: is that that the G action has sub-exponential growth of derivatives. Okay, and this means the definition is that for every epsilon, and there exists some constant, such that if you look at the how an element G, so this is true for all G. For all G, you look at how this is acting on the fiber, the derivatives are not growing too much, are growing less than constant times e to the epsilon G. And here is, this is the max over all P in M alpha. Okay? So maybe just see, if you want to keep this simple, just like think that instead of the action of SL and C, you just have an action of G, of SL and R. And so this implies, for example, that so what would be a non-example of this is, like, for example, you have an element acting on M alpha, and this has some fixed hyperbolic point. So if you have a hyperbolic fixed point, the derivatives of this element, the maximum derivative, is growing like exponentially, right? Even if it was just 1 point and the rest was like kind of elliptic behavior. So basically, yeah, this is a big constraint. Okay. Okay, so I'll first describe the average procedure that is going to give me my invariant metric is some straightening of like property T, and this is due to Laforgue. This is Vanson Laforgue, and is strong property T, and it states the following. Says that if you have some action of your group G in some Hilbert space. Oh, no, sorry. I'll put it differently because otherwise. So it says that there exists this epsilon, and here is for G equals SLNR. Just for this group, it says that there exists some epsilon 0, such that for every representation of G in some acting on a Hilbert space, that is not necessarily isometric, but is close to being isometric, such that the representation, so the norm of every element is, here is the norm of the bounded operators are smaller than some constant times e to the epsilon G. So it's very similar to this. Then if you compute the spherical averages, so this is a sphere on G, center at the origin, let's say. And if you take any element of your Hilbert space, so for us it's going to be, I take some metric, and in some Hilbert space of metrics, this thing is going to converge to some element of this and of the vector space that is actually this is a fix by G, by the G action. Okay. Okay, so but well, this might be a priori just 0 if there were no other fixed points. So for if you have a representation of a Hilbert space with no fixed points, the averages converge to 0. But so for us, or for me, the H is going to be some Sobolev space of metrics, and the action in this space of matrix is going to be just bounded in this nice way, just because I have like some nice bound on the derivatives, how the derivative is like changing a metric for any element of G. Okay. Yeah, so now I'll try to explain a little bit how to get like this sub-exponential growth of derivatives. So yeah, I'll call this theorem 2. Theorem 2. So I'll just put the idea of theorem 2. Idea of theorem 2 is that if is by contradiction. So you assume such by contradiction. Okay. So if such growth didn't exist, then well, I'll just write like there is like some hyperbolic behavior. I'll explain if I have time what is this, some hyperbolic behavior for the G action, for G action. And then this is going to translate into a measure, or then this is going to existence of mu measure invariant. So by some A in this Cartan subgroup that has some hyperbolic behavior, and this is like has non-zero Lyapunov exponent. So I'll try to explain a little bit what is this. Okay, and then there's going to be like some maybe like one of the main ingredients apart from this, that is some results from measure rigidity to upgrade this measure to a G invariant measure on M alpha that has non-zero Lyapunov exponents. And then you get a contradiction from Zimmer cocycle superrigidity, because Zimmer cocycle superrigidity says more or less that if you have an invariant measure, then the action in the measurable sense looks isometric. But this thing says that the action in the measurable sense doesn't look isometric, but there's like some expansion and contraction. But of course, I haven't defined what's a Lyapunov exponent, right? So this probably doesn't make much sense. So what I'll try to maybe say is what is like this. I'll try to explain what is this measure rigidity. That it explains a lot of the behavior of, or like all these rigidity theorems, and maybe if I have time, I'll try to say how to obtain this measure that is invariant. This is kind of an easy thing actually. This is the easy, and this is like super easy, and this is like super hard in my opinion. But so I'll talk about like this measure rigidity. So measure rigidity. So here I have like this action of A. A was some abelian subgroup acting on. So A acting first. I'll start with A acting on G mod gamma. Okay. So in the case where G is SL2R, then this action A is just in the right by right multiplication is just A is just the geodesic flow. In this case, you have this, and this is geodesic flow. Okay. So well, maybe something to have in mind is that G is, there is this decomposition, KAK. So in SL2R, the K is just, you take a vector in the tangent bundle of hyperbolic space, and the K just rotate the vector. The A flows the vector like in hyperbolic, like as a geodesic. So you can see that you can get from any vector to any other vector just like K, A, K, right? So, well, so basically the whole G action is just encoded in the action of A. So this is when n is smaller than 2. So this has like this is a hyperbolic behavior, but when n is greater than or equal than 2, when n is greater or equal than 3, then this is A has, that is just this, is a higher rank abelian hyperbolic action. So any element of A is going to be acting here. So it's a hyperbolic action of higher rank. And what is called like this, and maybe like an analogy that it kind of helps me to understand this is that this action. So there's like another example of, and this has like some rigidity properties. So I'll properties. So I'll state it first with another example. That is, when you have the action of multiplication by 2 and multiplication by 3 on the circle. Okay. So in that case, this is like a C2 action in the circle, and I'll state the there's like this Furstenberg conjecture that says that if you have that any invariant measure, on S1, any cross 2 multiplication by 2 multiplication by 3 invariant measure on S1 is either Lebesgue, because the Lebesgue measure is preserved by this thing, or is just supported in a finite orbit, or supported in a finite orbit. So there are not many measures that are invariant under these two things at the same time. But if you just look at one, then this is just conjugate to the shift. So there are like plenty, but okay. So in this case, there's like something called Margolis conjecture that is saying that if you have a invariant measure on SLN R mod SLN Z, okay, then this measure is either then mu is Lebesgue or Haar, or is supported in a torus T to the n minus 1. So if n equals 2, like what would be a torus? It would be just a geodesic in the hyperbolic surface. But here there's like this kind of two-dimensional thing, torus, the flat torus. Okay. So let's see. So I'll state the theorem. So there is like this kind of program due to Katok to understand like all the actions of higher rank abelian groups that have like some hyperbolicity. Okay? And maybe the theorem that is going to make us like have just an invariant measure, just invariant measure just by one of the elements to get an invariant measure for more elements is the following theorem of, this is Rodriguez-Hertz, Brown, and Shearing-Wang. And it says that if the dimension of M is less than n minus 1, then any measure, any A invariant measure on M alpha, so in this suspension, is invariant, is G invariant, provided that is kind of similar to this one, apart from the torus, but provided that the measure mu projects to Haar in the base, projects to Haar measure on G mod gamma. Okay, so this was fibering over this. So whatever measure you have on this mu alpha, like projects to some measure on G mod gamma. So if this measure was just Haar, and it typically is going to be Haar because of this theorem, then that measure was immediately G invariant. And A invariant measures are really easy to find because A is amenable, abelian, right? So you can find A invariant measures very easy. So I'll state. So this is the second part that I wanted to. And now I'll talk about just this part of what's some hyperbolic behavior and how to get a measure and what's a non-zero Lyapunov exponent, if I have time. But I'll. Oh, maybe I shouldn't erase this one. let's see. So the abelian, this thing is just, if the theorem was not true, this thing was not true, right? Then because I told you that G was KAK, and the action A is the important one, right? So I'll mention this fact of this elementary fact, but well, it's not so elementary, but it's elementary for the people in the hyperbolic dynamics. That is that if there exists a sequence of points xn, or sorry. So suppose I have f a diffeo, let's say n to n, and suppose there exists a sequence of points xn in your manifold n that where you see like some exponential growth. So some exponential growth, meaning the derivative is growing exponentially here for some lambda n. Okay, the conclusion is that there exists a measure mu, measure f invariant, that has a non-zero Lyapunov exponent. So what's a Lyapunov exponent? I'll explain that. If you have an f, and here is preserving ergodic measure. Oh, no, here nothing. There is no measure. That's the thing here. We started with no measure, and we got like a measure. So it's just coming from this elementary fact. But I'll state what is the definition of Lyapunov exponent. That is, if you have fn n and this preserving ergodic measure mu, then for almost every point in your manifold, there is a decomposition of the manifold of the tangent space into invariant subspaces, such that these subspaces are either like contracted at an exponential rate or expanded at an exponential rate. And so there exist some numbers, lambda 1, lambda 2, lambda n. These are called the Lyapunov exponents. And then if you take some vector here, then for all v in vi, then this vector is going to grow with with exactly the speed lambda I exponentially. Okay, so an example of this could be like for example when you have like this the 2-1 an Anosov map of the torus, 2-1-1 acting on T2. That is contracting one direction and expanding the other direction in the torus. So I think let me see if I have more time, but no, yes. The left-hand side.
The left-hand side of the left-hand statement, we have a
Lambda, yes. Yes. Oh, yeah. Sorry. Yes. Lambda is positive. Yeah, it's growing exponentially. Yeah, you get one non-zero positive Lyapunov exponent greater than alpha. Okay? Greater or equal than alpha. Yeah, well, one easy case, like if I have a fixed point that is hyperbolic, then the measure that you get is just that fixed point. And the tangent, and the splitting in the tangent space is just the usual, like it's the splitting of the tangent space of a hyperbolic map.
So in this theorem, do you know does one conclude any more like the action of F preserves the decomposition?
Oh, yes. Sorry, this is super important. This is super important. Sorry. That is that this decomposition is F invariant. This decomposition is F invariant, but the problem is that it's not a continuous decomposition. That this decomposition is just a measurable decomposition. Okay? So it works for any diffeo, but it's just measurable, and yeah. Yeah, so this problem, I guess, is one of these. The difficulties is just, everything is true in the measured sense, and everything is false in the continuous sense, and you want to go there. So that's an illustration of that, I guess. Yeah, and that's it. Okay. Yeah.
In your main theorem, can you restrict